Sweet. Okay. All right. Welcome everybody to lecture 2 of 389E. We go through all the regular setup stuff, so we're gonna go ahead and get started into some actual Minecraft business. So, um, this is where it gets, I guess, actually interesting. So, some general administrivia to begin with. Um, okay, so for the installation and setup of 389E, I saw a message in the Discord last night about like crashing. Whenever you launch it, you should probably let us know about that. Um, and or like more specifically, like what's happening, or if you've got some updates or been able to launch it. But if anybody hasn't been able to, just hit us up and we'll definitely get to helping you out because that is a necessity for this class. You cannot go forward in this class without installing the 389E Minecraft mod, the circuitry mod. So I guess this is a quick reminder if you haven't already gotten started on it, please get the installation kind of set up and done today. And we're just saying that so you've got enough time to, reach out to us. And I'll try to get the messages today. Can't guarantee super quick availability on the weekend, but we got you. So yes, that's what we got with that. And right now the submission for Project Zero that we talked about, because the CS department has been extraordinarily slow in allocating us a submit server. I think it has to do with the video game being in our class name. But our submission will be via a screenshot of you running the test, like the actual test command, the exact syntax. Um, Obviously, when you run the actual test, I think it's like test run, um, you take a screenshot of your tests passing there, and that should be perfectly fine for an actual submission. I didn't put in the slides, but to take a screenshot in Minecraft, I believe it's like F1 or F2. There is an F key command that does takes a screenshot and dumps it in a screenshots folder.
If you're lazy
Um,
like me, you could also just pull out your phone, take a picture of your screen, and upload that.
oh yeah, that's also perfectly fine. As long as we can like see that you did it. And of course, keep checking the course website. I've updated it for today and after today's presentation. The slides and the webcast will be put up simultaneously right after they finish processing and I get to it. Um, Along with the project, which will be as soon as it drops on Discord, we'll throw it up on the course website as well. So stay tuned for that. Remember, the way we handle projects in this class is Project Zero is due this upcoming Monday, and Project One will be coming out pretty soon. All you have to do is turn that in, not the coming Monday, but the following Monday. So you have a little over a week for what Project One will be. Cool. Well, I don't have my phone with me, but I would use that to check. Um, I guess also, well, I guess Ashwath will get your questions and lecture questions if you've got them.
Yep, I have my phone out looking at it, so.
Oh, perfect. Thanks, man. Alrighty. So announcements. Project one. So the conceptual knowledge in today's lecture will be provided to you kind of at face value here, and then we've got some stuff in the online textbook. I put a question mark there, just checking if that's actually useful for anybody. But that's like more actual background on the conceptual stuff that we're covering today. And of course, you already know that the project spec will be coming out post haste, so soon. So yeah, feel free to use either today's lecture for the baseline stuff, and then if you need some more review and some more in-depth, feel free to hit up that online textbook. It should be linked on the course website under week two's lecture and reading. So let me know if you can find it. We'll get you set up, but hopefully it should be pretty easy to click through and grab. Okay. That being said, all of our administrivia is kind of done with, so we'll talk a little bit about inputs and outputs and some theory stuff in Minecraft. So here's some basic stuff that you probably already know. I'm assuming everybody here has taken or is taking CMSC389E. And at this point in the semester, if you are taking it right now, you should be getting into understanding the basic logic gates. So right off the bat, actually, is anybody still taking 250 right now? Just curious. I feel like it's a prereq, but it could also be a correc.
I think it's a correc, but even then, I think 250 should have started with this stuff, right? So we should be okay.
Perfecto. Okay. Excellent. So we've seen the logic gates before. We're gonna go ahead and assume that. And most advanced gates, right? If you've heard of like NOR or like XNOR, are just they can be made with combinations of these gates. So we're gonna focus on the four basic logic gates today, and kind of build forward off of that, right? And as we look at things like these logic gates and go into how to build them, I want to talk a little bit about the characteristics of them, and sort of move forward from there. So from a very theoretical standpoint, we know that all of these gates, AND or XOR, require two inputs and produce one output, with the NOT gate being the exception since it's the inverter, right? And they are the absolute most basic constructs of the Redstone circuits we will be building in this class. I had that diagram previously of the full stack. I guess it was in the previous lecture, right, where we have these things like logic gates. And if you know a little bit of computer architecture, essentially logic gates are what, you use to implement a very low level like data path and these execution units for a CPU. And eventually that CPU, is the thing that processes, machine code, which machine code is produced as a result of assembly being compiled into machine code, and then you can kind of go up the stack from there. From there on out, CMSC316 kind of has you covered, and I would say here what we're kind of doing is a strange little analog to like 411. So that being said, we've got some more info. I usually, I mean, before I would talk about the logic gates and the actual like functions of each, but I'm assuming we kind of all know that already. If you want a review or a refresher on that, the online textbook sections linked and the lecture resources have all the information that you could want. And of course there are, as you can imagine, very easy ways to represent these using Minecraft's built-in redstone mechanics, which is always nifty. Um, we've got a little chapter in the textbook about redstone again, in addition to the video that we posted last week. So how can we take our understanding of logic gates and translate it into Redstone? And at this point, I would say if you are still kind of very new to Redstone, feel free to watch that Redstone Basics video that I put up on the course website last week. It should be under week one. So now we're kind of assuming that you have this kind of basic understanding of these logic gates from 250, so the purely theoretical understanding of those, and a little bit of Redstone. So we're going to go ahead and go step by step and make clear connections with Redstone concepts along the way. So we're going to bridge the gap between these two islands of knowledge that you hopefully have a little bit of right around now. So from a theoretical standpoint, the input for a logic gate is composed of one or two values, right? Now it looks kind of weird and abstract. We got this little two red wires going on the right side here in this diagram, right? And you can kind of think of those as the two inputs to a logic gate, right? And they can either be true or false. So let's go ahead and represent these inputs how we know in Minecraft. So as redstone wires, right? Assuming that a wire with the current coming through it is true and a wire without the current going through it is false. You'll see the same sort of structure replicated in Project Zero, right? Where you have to implement a simple inverted circuit. So we've got the state for off, and then how we'll describe on is like this. So you can see we're kind of going back and forth here between the two. But you can see on is lit up and off is just, the regular state of redstone. All right. So assuming this, can we think of outputs in the same way? And the quick answer is yes, we totally can, right? Output can be represented by a single redstone wire coming out of our logic gate, right? So if the wire carries current, it has a state of true. And if that wire does not carry current, so if it's not lit, it has a state of false, right? So that's kind of the simplest way we can explain it. And to put those two together, here's what we have so far, right? A way to represent input and output for our logic gates using redstone wires. So essentially we're saying, we got two redstone wires coming in, we got some random stuff happening to both those wires, and then eventually one redstone wire should come out, right? So for AND, you could have both of these have to be on in order for this to be on, right? Or for XOR, only one of the two should be on if you want the output to be on. If both are on, you're going to have an off output, and if both are off, you're going to have an off output. So, I just figured we'd introduce the input and output first so that we could kind of black box the structure and function in the middle and talk a little bit about that after. So, basic stuff with the input and output. Again, feel free to throw in questions in that lecture chat, and Ashwat will go ahead and interrupt me, and it should be no problem. So, It's an interactive class experience, or so I've been told. Okay, so now that we've got that abstraction built, right? We got the inputs and outputs covered. Let's go ahead and get what's in the question marks right here. Um, now that we've managed the sort of infrastructure needed for the rest of it. So the basic logic gates. Um, let's figure out what goes into the mystery box when we want to build these four logic gates, right? And of course, I'm only focusing on these four because we talked about how earlier you could just kind of use these four to be the foundation of the more quote unquote advanced logic gates, right? So we got your four conventional logic gates here, and we're going to figure out how to actually build them. Um, okay, so we have live demos on the course textbook to build all of these gates, and I'm going to go ahead and show you at the end of class when we do a little bit of a more live demonstration before project one. But we've also got a great YouTube video up on the course website about actually building each of these individual logic gates. So no worries if you don't catch up with the demo at the end of class. You can kind of watch and rewatch that video that we posted um, on the course website as well. So that's essentially what the case is there. And I think again we'll save the actual demo of building these to the end of class after all the instruction and talking is done. So that should be all good. Now, I think so. These live demos here, I am pretty positive this will open up a. Oh, okay, yeah, no. So the URL is old. Um, so I'll go ahead and change that when I upload the slides. But it'll essentially take you to a version of the online textbook that has a sort of live demo that you can look around in and see the different gates implemented. That's always a great resource. Again, I just want to add, so the NOT gate you've actually seen before, right? Let's talk quickly about each of them. And that's pretty simple. It's just a block and a torch, right? As for OR, you've kind of seen that already too. OR is basically just redstone wire. If you take some redstone wire and join these two inputs coming out, congratulations, you've got an OR gate. Talk a little bit more about that later. And the AND and XOR are a little bit more involved. But you'll see in the demos that you can put those together no problem. I do want to add that for XOR, and I mean for forthcoming designs, there are going to be multiple ways to implement certain very common circuits like XORs, adders, things like that. I would say go with whatever's comfortable for you, right? You'll end up memorizing a design or something, and that'll just kind of become second nature to you. So, whatever works. I think my XOR is like different from like Oshawat's XOR, but it's all in just whatever you're comfortable with. Um, so
Also,
yeah, those are
just
the
another
logic.
another disclaimer, real quick. A lot of like the designs online, if you look up like XOR Gate Minecraft or whatever, some of them will use like pistons and some more complicated designs. I would say don't use that just for the purposes of this class because the testing framework that we use has a lot of back end stuff that deals with delay, and the pistons will mess all that stuff up. So I'd say if you can try to stay with vanilla like blocks, redstone, repeaters, and torches. Those four should be good enough for all the gates in this class.
Yep, 100% agree. Thanks, Ashwath. I guess yeah, if you just don't use pistons, those have caused problems before, and there are ways to do circuit stuff without using pistons. So better to just stay away from those. Some people have asked in the past about using comparators as well. I guess you're welcome to. I personally don't, but they haven't caused any problems for us before. So I know that you can make an XOR gate a lot easier with a comparator. Um, that's totally fine. Cool. So this is basic logic gates. Again, probably won't dwell on them too much because I guess pretty simple stuff. No need to sit through slides about, all four of these. So we got some reading in the online textbook if you are so inclined or just want a quick review. So if you've taken 250 already, this is stuff you should already know. And of course, just some more information here. Oh, and Ashwath was at 250 TA. I think I mentioned that already. So should be pretty okay in terms of 250 background here. And feel free to ask if you need a refresher or if it's been a while since 250. So no problem there at all. Cool. And some new answers to remember. So a redstone torch, when placed correctly, will invert current, right? Also, repeaters will extend current and act as diodes, right? Diodes are basically just a fancy way of saying they will allow current one way, but not allow current the other way. I'll demonstrate this actual diode use when I show you an OR gate a little bit later, right? And of course, like I mentioned earlier, you're welcome to use comparators, but it is not encouraged just because well, we haven't really tested the testing framework working entirely with comparators, but I'm assuming that it works. So no guarantees there. We haven't tested that exhaustively though. So yeah, that's the basic stuff. Those are some nuances to remember, and I think it'll become a little bit more clear when we do a demo or if you watch the video. All right. Now I want to talk a little bit about stuff that maybe might not have been immediately apparent when you were looking at this stuff in 250. And the idea of logical complements is one of them. I don't think they focus too much on that. Um, so let's talk about logical complements, right? So occasionally we have a gate or circuit that produces the exact opposite of what we want, right? In this case, all you have to do is use a logical complement of whatever gate or circuit you've got, right? Using the dot notation is less cumbersome sometimes, right? There's a little bit of a discussion about that on the online textbook, but essentially what I'm talking about is, so you know when you draw these diagrams, right? You have the AND gate, and if you add a little dot right in front of the AND gate, it becomes like a NAND, right? Kind of a shorthand for adding a little inverter right in front of it. That's essentially what I'm talking about, right? Um, so I want to kick us off with a little exercise we're kind of going to jump into. Um, and this is meant to be a sort of review of these gates if you haven't like, thought about them for a while. Um, but I invite you to make your old 250 TAs proud and construct an XOR gate using only ORs, ANDs, and NOTs, right? So, if you've got a second, if you've got a piece of paper and pencil, feel free to give this a go. I'll give you like a little bit over a minute just to mess around with this, right? And the goal here is not just to go willy-nilly and throw a bunch of gates together to produce an XOR gate, right? Because I mean, it's very possible to do this by tossing a bunch of different gates together and covering every case, but similar to writing code, you don't want to just add a bunch of if-else clauses all over the place to solve your problem, right? So try to be as efficient and elegant as possible. And keeping in mind that in real life, problems like this, are solved by making circuits by hand, and every piece has a cost, right? Um, Additionally, having more gates in general equals more build time. So learning to think efficiently is pretty important in terms of building with Minecraft, right? When you're building circuits as part of a manufacturing process, this could have drastic effects on cost and final output, right? Not to mention things like mean time to failure and things like that. More components generally means more potential issues. When you're working with Minecraft, um, this kind of just means, okay, more gates means a somewhat higher chance of contracting carpal tunnel or developing carpal tunnel earlier in life. So probably best to stay away from building a super duper crazy amount of gates. All right, that being said, I'll kind of get out of your hair and stop talking for a little bit so you can kind of take a look at this exercise. Um, yeah, we'll take this second to, if you have any questions, just throw them in the chat.
Yeah, if you've got a piece of paper next to you, try to do this by hand. It'll be good for like just as an exercise, or if not, you can just pop up like Microsoft Paint or whatever, and try to do it on your own. Or if you can just think about it and conceptually understand it, that works too.
Perfect, perfect. So we got some time. It shouldn't. So no worries if it's eating away at your brain. It's definitely something you gotta just kick your mind into gear to do. Um, but yeah, simplicity is key. If I were you, there are some like neat tactics you can go about to solve this problem. So I'll talk a little bit about that in a second. But just take a second here to wrap up and finish up if you're thinking of a thought. Cool, cool, okay. So at this point in time, some may be asking, why is something like this so important, right? You signed up for 389E, not 250. Um, and the answer was kind of already discussed, but the general idea of it is that, some gates can be built using other gates. So aside from the whole time saving thing, right? This is actually a fundamental piece of understanding that we're about to uncover here, right? Um, Knowing that we can build some gates with other gates kind of opens up a new world of possibilities here for us, right? Because if we can construct that XOR, um, that regular one of the four main gates using a few of the other gates, then this might get some people thinking, like, hey, what other gates can we build using these other gates, right? And this is what um, computer engineers thought about maybe, I don't know, 50, 60, I actually I have no clue. It's definitely more than 50, 60 years ago, but a very long time ago, right? Um, so this kind of brings us forward to something that we didn't cover in 250, these applications in computing, right? So let's talk about the NAND gate. Now this is a very strange transition because I don't think you really focused a lot on the NAND gate itself, right? And as it turns out, they are the most commonly found gates in computers. So whatever you're watching this lecture on right now on Discord, under whatever metal unibody plastic chassis that your keyboard is sitting on, you probably have a high abundance of NAND gates, right? And that's very weird to think about, but at a very low level, on like the lowest level, it probably is composed all of that. And of course, if you've heard names like NAND Flash, right, that might be a little familiar. It's called that because essentially it's constructed using those NAND gates. So I want to go ahead and pose the question like, why is that, right? So given that we have these four basic gates, and not or and XOR, why would NAND ever end up being one of the most popular gates at a very low level being used to implement functions on a computer? So the NAND gate is what we call functionally complete, right? So is the NOR gate. And at this point, if the NAND gate seems a little confusing to you, I would just quickly pull up the online textbook or the lecture slides. In fact, I can go ahead and pull them up right now. Let's see if I can. Yay, okay, excellent. So over here on it's also linked on the course website as well. But here's what the NAND gate looks like, right? So previously I mentioned, oh, by the way, can you see this?
Yeah, we can.
Oh, great. Okay, cool, cool. Um, this gate right here is essentially AND, except that it's got the inverter right at the front here to signify that the results of AND are being inverted, right? And you can see the truth table on the right here reflects that. So this is a very interesting gate because it's functionally complete, right? And we actually end up with a similar case with NOR over here, right? So again, you take a look at the truth table, it's essentially just OR, but inverted, right? Now, the very interesting thing about NAND and NOR that might not be immediately apparent is that these two gates can essentially be used to produce all the other gates, right? So you can make, specifically, you can make a NOT gate out of NAND gates. You can make an AND gate out of NAND gates. Sounds silly, but it's possible. You can make an XOR gate out of NAND gates. And of course, you can make OR out of NAND gates as well, right? And this might seem a little strange at first, like making gates with other gates. Why would that ever be very useful? But the thing is, we're also talking about applications in computing and manufacturing, right? And we can take a second to look at the complements here. On the left, we've got the NOT gate, replicated in NAND form. Here we've got the, I believe that's supposed to be AND. I got the little extra dot there, but this is AND replicated as a series of NAND gates, right? Where essentially it's just inverted twice. And over here, we got OR replicated as NAND gates, right? So pretty simple stuff. And this is XOR. It's a little bit more complicated, but this is how you would get it done with NAND gates, right? So, feel free to take a look at these diagrams in the lecture slides. And at this point, you might be thinking, okay, well, I get that we can make all these different gates with NAND gates, but especially when you get to things like XOR, or like OR or XOR, you end up using 4 gates to complete the functionality of one. That sounds a little egregious, a little extra, right? Especially if you say have to implement like 600 XOR gates that quadruples in size. So you can see there that right off the bat, at the outset, you might think that that's a massive inefficiency in terms of using just NAND gates. But here's the deal, right? If a gate is functionally complete, all other gates can be constructed using it. And in a fabrication process that was pretty common recently, I don't know if as of very late it's still very common, but NAND is smaller and faster to build than a NOR gate, right? And it turns out that when you're manufacturing these chips, um, what you want to be doing is building a housing to manufacture maybe like a bunch of NAND gates and just produce those instead of maybe having to come up with, okay, well, we have to build like 30% XOR gates, 10% just inverters, and the rest will have to be dedicated to just building AND gates, right? Instead of having to worry about that during the circuit fabrication process, you can focus on building just a NAND gate really well and really compact, knowing that this NAND gate can be used to produce all the other gates possible. So in other words, what I'm trying to say is since computers are composed of all of these four logic gates, right? Um, and since these four logic gates can be produced using NAND and NOR gates, essentially if you can build one NAND gate anywhere, that proves that you can build a computer, right? So that's a pretty big jump in logic there, but that's essentially what we're trying to say. Now, this seems a little weird and theory heavy, right? Oh, and of course, if I didn't mention earlier, it just turns out that NAND is smaller and faster to produce than NOR. That's why we prefer NAND over NOR, even though they're functionally the same. Right. So making that big logical jump, you might be thinking, hey, this is a bunch of weird theory stuff and computer architecture stuff. So how does that really apply to us? Well, we're going to leverage this fact to prove something fundamental in Minecraft, right? And of course, here's a little TLDR on the importance of the NAND gate itself, right? Because of these reasons, NAND gates are the pick over NOR gates for the universal gate that engineers use to build other gates and eventually other full-size circuits. So we go into a little bit more detail on the textbook itself, and you're free to take a look at that on your own time.
Just one little tidbit. Also,
Oh,
just for logistical reasons, back in the day when people were making these circuits, it turned out that the NAND gate was cheaper to build. And just to put this into like an analogy that college students can understand, if you go to Costco and buy a shit ton of ramen noodles, you can get it for cheap. But if you go to Target and buy them individually and like get certain things like in small quantities, it's obviously going to cost you more. So that was the same philosophy with NAND gates. You can just buy a ton of them, and you can use them for everything, as opposed to ordering a little bit of this, a little bit of that.
perfect. Yeah, excellent. Solid analogy. That's essentially what the idea was. Just cheaper to buy in bulk. Perfect. And now we're going to go ahead and segue over to applications of this, just what Oswald was mentioning, in Minecraft. So, making it kind of cheaper and stuff is really neat for computer applications. But it turns out in Minecraft, we don't really have to pay for building any of this stuff. So we save costs in other ways, right? But here's why NAND is so important for us in Minecraft. And the general idea is that, we're able to make a NAND gate in Minecraft, right? And thus far, you've kind of seen, okay, we're able to build an AND gate and build a NOT gate. So by building AND and putting a inverter in front of it, we're all good to go, right? And this is important in and of itself. The reason being, you don't really think of it as we can just build a NAND gate in Minecraft. It is because we can build a NAND gate in Minecraft that we have proven systematically that we are able to create a fully functional computer in Minecraft. So in other words, provided that we can create a NAND gate within the game, and knowing that the NAND gate can be used to replicate every other gate, and thusly, execution units and therefore like a data path for an instruction set architecture, and so on and so forth, going up the stack. We have thusly proven that by building one logic gate, right, or being able to build a logic gate, we can build a computer within Minecraft. Um, this is actually a very powerful idea. And it turns out that using this idea anywhere actually leads you to pretty neat conclusions. So other words for this idea of functionally complete, some people might have heard of Turing complete, right? It's the same notion. Um, and it turns out that this very powerful low-level idea of being able to build an AND gate, thusly being able to build a computer, has actually been leveraged for other like interesting purposes other than Minecraft. So there was actually a paper online of a guy who I think he figured out that PowerPoint was Turing complete or functionally complete. You could implement like some NAND logic in there using like conditionals and transitions. So there is a very simple computer dot like PPTX sitting around somewhere like a programmable computer in PowerPoint form and a neat paper about it. I guess we can take a look at that after class if you want to, but it's pretty neat. So essentially anything that lets you replicate this NAND logic is going to let you build a um, computer within itself, which is kind of neat because now that you have these NAND gate functionalities within computer programs, we kind of get to the idea like, we could go deeper. This essentially proves that we can, if we really wanted to, build a computer in Minecraft that can run Minecraft and thusly continue that loop forever and ever, which I think is pretty neat. So that's some food for thought. Um,
Wait,
yes, so
wait,
that's
what? What? Are we doing that?
well, okay, we're not going to do that. That's it's going to be like ridiculous and take a really long time, but it's theoretically possible, right? And that's what's important. We're going to be building a much more simple um, version of that computer because we are not masochists, but it is definitely possible. And there are some crazy YouTube videos of people building these large many-bit computers that you will actually be able to kind of follow along with them after you take this class. So, something neat to look forward to. Um, Now, does this mean for us that we will build everything using NAND gates in Minecraft, right? Considering that that's the industry standard, some of you may be led to think that this might be the way to go. The answer is no. That's completely ridiculous. In Minecraft, I mean, building NAND gates takes a little bit more effort um, than building like XOR or NOR. Now I say that's ridiculous, but actually, if you end up leveraging Minecraft's duplication abilities, right? Block duplication. Okay, by duplication I mean things like cloning, because I know dupe has another connotation in Minecraft. Um, you can actually end up using, so I know I have that's ridiculous on this slide, but if you are really inclined to do so, you can build everything with NAND gates in Minecraft, especially for your assignments. Feel free to if you are so inclined. It'd be cool to see that in a project. Um, but I say if you're building it by hand, it's kind of a ridiculous pursuit. Like no need to go out of your way to make the work more for you, considering that the only reason NAND gates became very popular in the first place was, like Ashwat said, to make costs a lot more manageable, and of course, it's just cheaper and faster to just produce like a crap ton of these things and then throw them all together, right? As opposed to producing a lot of different specialized gates with quotas for each of them. So it's important at this point to notice the subtle yet key differences between Minecraft and real life, in terms of digital logic, of course, and otherwise. Yes, I think if 2021 continues the way that it is, or that 2020 was, I'm probably going to move permanently to VR Minecraft and never come back. So good to keep these differences in mind. All right. Now we're going to talk a little bit about efficient circuit design, right? And this is where we bleed a little bit back into CMSC350, but I promise exercises like this are very important and they can end up saving you a lot of time when you're actually implementing or building in Minecraft. So if we want to create circuits that produce the output that we want, right, with as few components as possible, you can kind of think of it the same way as you did in 250, right? Where, maybe you're given a truth table or some inputs and outputs, and you're told, hey, replicate this using some logic gates, right? The only additional bit here is that now we're going to build the logic gates, right? So when discussing Boolean logic in Minecraft, we should think about the logic rules that come along with it. In other words, you can kind of think of these digital logic circuits as Boolean predicates, right? So a Boolean predicate, I guess if that sounds unfamiliar, it's essentially just these conjunction, disjunction, parentheses around them and stuff. And we'll give you an example in a second. But it turns out that if you've got a pretty complex looking predicate, right, you are totally welcome to use logic rules like modus ponens or whatever to perform I'm pretty sure that's not a real one actually, to perform simplifications on our circuits whenever needed. So on this slide itself, I've linked some of the Boolean logic simplification rules from at least when I took 250. I bet there's probably a version from when you took 250, but that link pretty much always works, hopefully. So feel free to take a look at that. And I'm going to go ahead and post it in the Discord because we will have somewhat of an exercise in a second. Whoop. Throw it in there. I'll put it in lecture questions. Zoop. Okay. But yeah, now you go ahead and give what I just talked about a try if you've got the time, right? So suppose you are given the following circuit, right? And my question to you is how would you go about simplifying this, right? So we've got a few steps that we can approach here. Notice that I've given you the graphical representation of the circuit, so that should be a way to kind of start you off there. Like, what can we do to simplify this? So if you don't already have like maybe that same piece of paper or like if you've got time to take out a piece of paper, if you just want to do it in your head, feel free. Um, but I encourage you to think about this, right? Because um, ideas like this are going to be very important when you end up start implementing these gates in Minecraft, right? And optimizing and cutting things down. So just some key things that I want to point out right at the outset. We've got, and I find it sometimes easier to read from right to left. Um, when you're going down here to kind of just describe the actual circuit that's being shown on screen. And of course, it looks like we have V coming in twice, so maybe some opportunity to simplify there, right? Well, I mean, I was about to do the old 250 TA, so if you wanted to add something or some superlative words of wisdom, I shouldn't take the opportunity away from you.
Nope, you're good. That's I have nothing more to add.
Cool. Awesome. Okay. Cool, cool. So if you've got a moment, feel free to take a look and kind of think about how this will go for you in terms of simplification, in terms of what you could use. And of course, I linked that thing in lecture questions for a reason. Just take a look at that, see if anything jumps out to you, makes sense as a good way to simplify this into perhaps a little easier circuit that still produces the same results. So give you a second to think about it.
Did you want us to like answer or just think about it?
Oh, I guess I would say go ahead and answer it like on a piece of paper yourself. Um, because I think I got the answer that I'll pull up on the next slide, and then we can kind of compare. Um, Either way, just to give everybody, because I feel like some people will just get it like that, and then some people have to think back to 250 and be like, oh, well, let's see. So, no worries. Thanks for asking.
Yeah.
Cool, cool. So we've kind of looked at this for a little while, and again, if you're just finishing up, some little tips and hints for you are like reading it backwards. You could say, looks like this is an OR of two AND gates, so you kind of get like an idea there. Um, General purpose like solution for this sort of thing would be to kind of write it out in Boolean predicate form, and from there on out, it gets very sort of simple to visually correlate that predicate with some of the rules that you've provided, and produce that answer. Correlate's not the right word, but you get the idea. So like I said, we'll write it out using Boolean logic, here representing the conjunctions and disjunctions with a character that we use to represent those, and using parentheses where needed in order to represent the precedence of the actual operations. So you can see here that we've simplified the diagram down to just A and B, disjunction B and C, right? I guess A and B or B and C, right? And when we apply the distributive law to get the following, you can see that we've actually gone down a significant amount. We are using, I guess, 33% less gate in the second diagram here, right? And you can see, just like we had the two B's here, if you rearrange them, put the B in the front, it becomes very easy to see that we can just use the distributive law here, or I guess it becomes a lot more apparent that we can use the distributive law to simplify the circuit down, only use the inputs once, and get the exact same functionality, except with less gate. And the idea here, this is a pretty, I guess, simple problem as far as these go compared to what 250 offers. But the idea here is very powerful. It's that, okay, sometimes we might have designs or you might come up with ideas that represent certain truth tables using a bunch of different gates, right? But before you even implement them or before you design them, in our case, before you put them into circuits in Minecraft, or in the case of industry, before you actually turn them into real circuits, right? You want to make sure that it's the most efficient possible. Why? Because just a second of thinking now could save you a minute of building and debugging later in Minecraft, right? Not to mention the extra space and the wrist health. So that's just a cool little bit there to think about. Key takeaways here: knowing the basics of Boolean logic kind of opens the door for us to make more advanced circuits, right? And to simplify those down. It's kind of like writing code, right? There are always brute force ways to do things. But once you kind of get an idea of simplification in logic, you can really pare it down and make it a lot easier to produce some of this stuff. So in general, understanding this idea of functional completeness just gives us the theoretical knowledge to know just how computers can be created in Minecraft, right? So I would say these are the two key takeaways of the lecture. I guess if you're going to walk out of this with anything at all, just remember these two bullet points. I mean, it is kind of, well, it's not early in the morning, but I guess here in California, it's kind of early. So, you know, I don't judge. And of course, Boolean logic rules are essential to designing circuits in the most efficient way possible. This saves time, money, and materials for us, very precious in the real world, and basically just saves us from carpal tunnel when we're working in Minecraft. So, you know, pretty solid benefits either way. Now we're going to talk a little bit, probably about Project One, which is kind of just a showcase for logic gates at this point, right? At this point, Ashwath, if you want to say anything about Project One, I can hand it over to you. And then I was thinking of maybe showing either a demo or just kind of going through the video in a little bit.
Yeah, sounds good. So basically, at a high level, Project One is just making these logic gates that we discussed today in Minecraft and getting you familiar with it, because you'll need to use them later, and it's definitely necessary for you to be able to think of, oh, I need to build an XOR gate, and not need to look at like a reference. I mean, obviously you can. It's not required that you memorize these or anything, but it's just good to intuitively know how to do this stuff in Minecraft, as well as the fact that every computer needs what's known as an ALU, arithmetic logic unit, which does all of these operations in the back end. Every computer has sort of a calculator that runs these things. When you tell Python to calculate 1 plus 3, it does its own like internal logic and calculates that for you. The same way, we do need some sort of thing for our 3-bit computer. So you will be making a 3-bit version of all of these gates. So what that essentially means for you for Project One is you'll be making 3 OR gates, 3 AND gates, 3 NOT gates, and 3 XOR gates. So hopefully that sort of muscle memory and repetition will be helpful for you going forward when we get to more complex circuits, but this project should not be too much of a chore, considering I think Aki is about to show you exactly what you should be doing on a 1-bit level, and all you have to do is extend that to 3 bits.
Solid, all right. Cool. This is when I go on my adventure of doing the screen share thing. So let me give it a go. I'm gonna go ahead and stop streaming. And then talk a little bit about, okay, well, number one, on the course website, you will see, hopefully it's up already. I'm gonna go ahead and pull it up myself for a second here, but okay, yes, there is a video linked called Building Logic Gates in Minecraft. So, you know, you can feel free to go ahead and take a look at that as well. It'll be in the lecture as well, I assume. But it'll also be in the Building Logic Gates for Minecraft video. So feel free to take a look. All right. And now I'm going to go ahead and launch Minecraft and share the screen. So we'll see if that works. I did some testing yesterday and it should, but fingers crossed here. Excellent. So in the interest of time, I'll just quickly go through or not and XOR should be explained in more depth in the YouTube video. Okay, let's see if this works. Yeah, Ashwath, can you see that?
Yep, we can. Good stuff.
Yeah, amazing. Okay. Excellent. It took a second a while back. All right, neat. Okay, so this is just a world that I Redstone ready configured for 389. This is the stuff from the video last time. Cool, and we'll kind of just talk about how to build these basic logic gates, right? So the first thing I want to touch on is the in-out nodes that you've kind of hopefully become familiar with. Basically, just function as generators for current, right? So if you've got like a empty redstone wire that doesn't have any current running through it, you can go ahead and put a torch next to it, right? And it'll provide current. The in-out nodes essentially just do that. They provide current, and over here at like this end, I would kind of use the analog of a torch, of a lamp, sorry. They observe the current and change state based on whether or not current is coming in, right? So if there's no current coming in, lamp goes off. And that's how we're gonna kind of look at the results of input and output, at least when doing these like little lecture demos. But input output blocks are basically the exact same in their sort of functionality. Okay, so moving on to logic gates. First thing I want to talk about is the OR gate, right? The NOT gate we already went over, so I'll go ahead and spare you the description, right? But the OR gate is actually quite simple if you think about it, right? It's essentially just something like this, right? You can see here that, actually, I'll come around on this side so we can have a left and right analog. But over here would be our output, right? And we can quickly see that, no, we will not be graded on how efficient our circuits are, so no worries. It's just kind of like yeah, no problem. It's more of a, like a less effort for you kind of thing. You can see here that if we provide an input on this side, the output is on. If we provide an input on this side, the output is on. And of course, if we provide both, the output will be on regardless. The one reason I wanted to point out the OR gate to you when building it is that we can use redstone repeaters as diodes, like I mentioned in the presentation, right? So if you go ahead and place these repeaters here, you'll notice that they prevent current backflow. In other words, bringing current from here no longer powers this, right? So the current doesn't go backwards. And bringing in current from here no longer powers this. So this could be useful when you have some more like, involved circuits. Like for example, if you maybe had, suppose we had no repeaters here and we had some other logic gate here that I'm not sure for whatever reason had some connection and you didn't want it going back this way or backwards into whatever logic you had there. It just makes it a lot easier to have the repeaters there and have the peace of mind that no backflow will ever occur. So I think it's a good inclusion for your design. Oh, so the reason we can't put the repeater at the intersection is because we can't have more than one thing feed into the repeater, right? So you can see if we attempt to do that, or actually, if what you were saying is put the repeater right here, now we would save a repeater by doing this, however, it wouldn't achieve the same functionality, because if you see here, the repeater acts as a diode, but it only acts as a diode right here, right? So it doesn't stop them from producing backflow, which was the reason we put it there in the first place. So if we put it here as well, you can see that the circuit just doesn't work. But yeah, great question. So that's the OR gate, and I'll quickly show you the AND gate as well, because I know we're running out of time here. The AND gate is just slightly more complicated, but again, once you like build it a few times, it kind of becomes muscle memory. So again, we've got our inputs, right? So just like we talked about in lecture, you can see we got our inputs and we're gonna have our output here. So it's kind of neat to sort of see the analogs of the diagram in lecture and then see the actual representation in Minecraft right afterward. But here we go. I'm going to use any block. I use the light blue concrete here just to have some contrast. And this is how you build an AND gate, right? So you'll need 2 torches here on top, some redstone wire in the middle, and this right here. And it turns out this strange little design is actually how you produce an AND gate in Minecraft, right? And you can see that, well, kind of prove that it works. Put down a torch here, no output, right? Put down another additional torch here at the second input, and we suddenly have output. We get rid of one of the inputs, however, and we realize that we no longer have output being on. So you can see this is a neat little way to build an AND gate within Minecraft. And we're running out of time. The XOR gate is slightly more involved, but I go over it in detail on the YouTube video linked on the course website. And of course, you already learned how to build a NOT gate, which we can kind of see over here. Right, so again, inverter, NOT gate, same thing. Cool. And that's all for the live demo this week. So we'll go ahead and close the stream. Cool. We are rounding out just at 11:51 a.m. in East Coast time.
If anyone has any last minute questions, feel free to drop them in. But I think otherwise we are running a little bit over, so I think.
Go for it.
Yeah. As always, thank you guys for showing up.
Thank you for having us.
Yeah, no worries.
When are you gonna have it up, the project PDF?
By the end of today, like similar to the last project, we'll try to get them out like right after lecture.
Can you like ping us? Like,
Yep, I'm gonna create the role with the notifications that I put in the announcements channel last time, and I'll ping everyone who reacted to that message.
Okay, thank you.
I was the one with trouble with Forge, so I was just wondering when a good time would be to get help is.
If you're going to, go for it.
No, I was just okay. So what your bug was? You're getting an error launching Forge itself.
Yeah, so I have it installed and it recognizes where my Minecraft is, and when I try to run the Forge profile, it just keeps on saying exit code 0.